Alright, now we're going to look at some practice problems. Yay. So in our practice problems, we first look at this system. So this is the system we're looking at. This is the state model for that system. And I'm going to use now this code here to, okay, so notice here I took my transfer function, started with the transfer function, got a state space model from that transfer function. So actually I'm using this state space model, which is not actually the same as this state space model, or it might not be the same. So it actually might be the same, but depending on how they implement this transfer function to state space, you might get slightly different value. So if we use this Ackermann's command to place the poles at -1, -1, -3.5, -2.5, those are all stable poles, and the observer poles to be placed them further to the left, -10, -11, -12, -13, we can get these. This is my state feedback gain, this is my observer gain that I get. So that will give us a stable state feedback with these poles, with these closed loop eigenvalues. So using a state feedback, using that, and if we use a full order observer, then we use this observer gain, and we get the desired eigenvalues. If now we choose F to have these eigenvalues, F to be a diagonal matrix with these eigenvalues, we can use this command that I've created. So you can find that on the Canvas site or the website. You can find this M file. And reduced order observer. So here you pass it the ABC matrices, you give it the F matrix and the K matrix. So the K matrix, and it will return the reduced order L. So remember that the two L's are not the same. It will return a KZ and KY. It'll also return the T matrix if you want the T matrix. And so these are all the things that get returned when we run this code. So this then will give us the reduced order observer, and I get the observer gains LR, KZ, and KY. Alright, so now I can use this Simulink diagram to simulate the system. Okay, so I'm going to simulate the system. So this scope is going to basically look at the output of the system. It's going to look at the step input that's being applied. So this is a constant, which is basically a step input. And then we're going to look at the output of the system using a reduced order observer. Okay, using a reduced order observer. And because of the fact that MATLAB assumes that you might have a D matrix in these, it has a problem with that algebraic loop we talked about. And so if you use a slight delay, which is a memory, you can avoid that situation. Okay. So that's what we're doing. So now what do we have in these different state space matrix things here? So these two guys are actually the same because that's the system. Then so what are we putting in here and here to implement the full order observer and the reduced order observer? Okay, so here's what we have. So in this block we have A, B, C, and 0. So our D matrix is 0. I'm going to put some initial condition. Here I put a random initial condition on the system. And it's the same. I'm putting the same initial condition on both of these guys. For this guy, for this observer, I'm using A minus LC as my A matrix. L and B, remember we have two inputs now. We have the output of the system and the input of the system, L and B. Our output is K, so our C matrix. So actually, even though I show a gain here, this is actually a gain of 1. But our K here takes the state feedback estimates and puts them out directly. So 0 initial conditions. D matrix is 0 associated with each of these two columns. For this part, we use F as the A matrix. Here we use LR and TB as the B matrix. KZ as the output for this system, and then we have KY. So KZ and K. Remember, we have two inputs coming in, so KZ times gets multiplied times Y, 0 times the U. Okay, so these are the state models that we use to simulate the system. Okay, and when we simulate it, boom, this is what we get. So what's going on here? So this one is the input, and then these two signals, the output of these two systems, each with their own controller, they follow this. They do this. Okay, so the magenta is this guy, and the cyan is this guy. So we can see that we have a more radical response when we use a reduced order observer, more radical peaking. Remember, we had a mismatch of initial conditions, so the observer had to catch up, and then eventually they both settle out to the same value. And I have a question for you. What's wrong with this picture? What's wrong with this picture? So we've gone through, we've computed state feedback gains, observer feedback gains, we did the reduced order observer, and yet what's going on here? When we look at this output, we see that neither of these two systems is tracking the step input. That's what's wrong with this picture. And the reason they're not tracking that input is because we haven't actually designed that to be the case. We haven't designed it to track that. We've just designed the observer and the state feedback gain to be stable. We haven't designed the system to be able to track anything. So that's what's wrong with this picture. Now we could modify this if we wanted to, but I'm going to save this problem for another lecture, because we will talk about then how to track, incorporate observers in order to be able to track signals. But that's for another lecture. So stay tuned for that.